So I'd like to talk about representation theory of W-algebras and Higgs branch conjecture. So what W-algebras? W-algebras are certain generalization of infinite-dimensional Lie algebras, such as affine Katsumudi Lie algebras and the Virasoro algebra. And W-algebra can be also considered as affinizations of finite W-algebras introduced by Prime, which are natural quantizations of Srodoi slices. And W-algebras appeared in 80s in physics in the study of the two-dimensional conformal field theories. And the W-algebra are closely connected with other area of mathematics, such as integrable systems and geometric Lagrange program and four-dimensional gauge theory. Okay, let me introduce you one example of a W-algebra. So this is Zamorozhov's W3 algebra, which so this is the first non-trivial W-algebra. So this has the following generators, Ln and Wn. And this is the central element. So this generators generates the so-called Virasoro algebra. So W3 contains Virasoro algebra as its sub-algebra. And computation relation between Ln and Wn is this. It's quite simple. But the computation relation between Wm and Wn is quite complicated and looks strange. So one of the reasons is that we have this singularity. We have 22 plus 5c. Where C is the central element in the denominator, but this singularity can be removed by redefining generators. So this is not really a problem, but the element here, which is defined as this one, this has an infinite sum with a quadratic term. So what is defined here is not really a Lie algebra, also W-algebra generalization of Lie algebra, but vertex algebras. So this commutation relation is a special case of so-called Boucher's relation, which appear in Lie algebras, in vertex algebras. Anyway, so commutation relation is quite complicated, but we can make sense of representation by imposing this kind of condition. If we impose this condition, then this infinite sum becomes a finite sum on a representation. So it makes sense to talk about representation. So in particular, you can define highest weight representation of the W3 as usual, and this of course satisfies this relation. And you can talk about the highest weight representation. And for a highest weight representation of W3 algebra, you can define the normalized character as this. So this makes sense, and so you can try to determine this character. And you can do this for any other vertex algebras, for example, other W-algebras. So in general, W-algebra is defined by means of the so-called quantized Dirichlet-Sokolov reduction, which is a version of Hamiltonian reduction, which was introduced by Fegi and Frenkel and generalized by Katsuru and Wakimoto. So for each simple Lie algebra and its nilpotent element, you define certain vertex algebra as by some Hamiltonian reduction. So this is a biaristic homology of the Dirichlet-Sokolov reduction associated with these datas. And this is a version of the algebra cohomology. And because Hamilton reduction can be described in terms of realistic cohomology in general, so this is a natural analog of a Hamilton reduction for the affine setting. And VKG is the universal affine vertex algebra, which is a vertex algebra correspond to the affine Katsumudi algebra associated with G. And I'll talk about a little bit later. So anyway, so for this data, you define certain family of algebra or vertex algebras. So for example, if nilpotent element is 0, we don't do Hamiltonian reduction. So this is just a vertex algebra associated with affine Katsumudi algebra. And the representation of this double vertex algebra is the same as the representation of affine algebra of this given level K. So in this sense, double algebra contains affine Katsumudi algebras. And if you consider the simplest case SL2 with non-trivial nilpotent element, what you get is a Virasoro algebra, or Virasoro vertex algebra corresponding to the Virasoro algebra. So, and the representation of this vertex algebra is the same as the representation of a Virasoro algebra. So in this sense, double algebra contains also the Virasoro vertex algebra. And if you consider SL3 case, what you get is a W3 algebra, or the vertex algebra associated with this W3. And so you can, so if you consider SLN, this is also called Fatih kind of WN algebra. And so this double algebra form quite a large family of vertex algebra, and in fact, it's known by Katsuran and Wakimoto that almost all superconformal algebras are realized as a double algebra associated with some Lie superalgebra. So definition naturally extends to the setting of Lie superalgebra and minimal nilpotent element. So a structure of the double algebra is quite complicated, as I said. And it gets more complicated as the dimension of the orbit of this nilpotent orbit grows. So this minimal case is the simplest case. And in this case, you can describe the double algebra by generators and relations, or OPs. However, representation of more general double algebra by presentation of more general double algebra by generators and relations are not known in general, even for this well-known Fatih kind of WN algebra case. Anyway, although we don't know the commutation relation, and we want to describe its representation, so how we can describe? So the double algebra is defined by certain Hamiltonian reduction called the Dunning-Sokolov reduction. And this definition is nice because it gives rise to the following functor. So you just replace coefficient by any VKG mod, which is the same as J hat mod of level K. And you hope that this functor behaves well, and the one hope that this functor gives enough information for double algebras. And so this is, as I said, this is the same as a category of module of the affine Katsumudi algebra. So in particular, the category O of G hat of level K can be considered as a full subcategory of this category. And so the simple object here, the irreducible highest weight representation of G hat with some highest weight lambda, which I denote by L lambda. Now, this functor behaves best if nilpotent element is minimal. In fact, in this case, you have the vanishing of cohomology for all objects in this highest weight category. So you have the exact functor from the category of category O to the category of module of minimal double algebra. And moreover, the image of simple is 0 or simple. And moreover, any irreducible highest weight representation of minimal double algebra arises in this way. So what this means? This means by the Euler-Poincaré principle, the character of this cohomology is expressed in terms of the character of a complex, which is so it's written in terms of the character of the coefficient, which is known by a result of Kashiwara and Tanisaki. So we get the character of all irreducible highest representation of a minimal double algebras. And I should remark this theorem holds for any, so even for these superalgebras. So once you know the character of irreducible highest representation for the superalgebra, you get the character of all important superconformal algebra such as n equal 2, n equal 3, n equal 4, big N equal 4, superconformal algebra for free. But at the moment we don't know the character of the character of this affine D superalgebra is not known yet. Anyway, so the functor behaves quite well for the minimal nilpotent element. And but historically, the double algebra associated with the principal nilpotent element were studied extensively, and which I call principal double algebras. And in this case, unfortunately, the Dirichlet-Sokolov reduction functor is not exact in general, but you can modify slightly this functor to get a similar result. Namely, we get a character of all irreducible highest representation of principal double algebras, including to the W3 algebra I showed in the beginning. And so this in particular proves the conjecture of Frenkel-Katsuba-Kimoto on the existence of a modular invariance representation of double algebras. And also the similar holds for all nilpotent element in type A. Okay, so at least for the minimal nilpotent element case and principal nilpotent case and type A case, we have good knowledge of representation of double algebras. So now we want to talk about application. So for this, the following I would like to recall the following important result of Zhu. A theorem of Zhu says if V is a nice, which I explain later, vertex algebra, then the character of any simple module converges to a holomorphic function on the upper half plane, and for the space spanned by the character is invariant under the action of SL2D. So they form a vector valued modular function. And in fact, and also one shows the category of representation of a nice vertex algebra form a modular tensor category, which gives rise to an invariant of 3 manifolds. So as soon as you get a nice vertex algebra, you get this kind of a nice property for free. And here, a nice vertex algebra is called nice if it satisfies certain finiteness condition called Leith, which is the same as so any vertex algebra canonically filtered. So you can take associated graded, which is in particular commutative algebra. So you can consider it a spectrum. The condition is that spectrum is 0, or 0 dimensional. So this is a natural analog of finite dimensional generality condition. And also V is rational, which means that any representation, any representation is completely reducible. So, if we satisfy these two conditions, we get this nice property. But of course, it's difficult to find new vertex algebra satisfying these conditions. Okay, let me show you an example, nice vertex algebra. The universal affine vertex algebra is not this at all, because by definition it was an induced representation. So as a vector space, it has this size. And so the filtration here is the same as the PBW filtration here. So the ring is just a symmetric algebra of T inverse dt inverse, which can be naturally identified on the function, the arc space of this star, which is infinite dimensional. So this is not this at all. But if you take a simple quotient of this vertex algebra, and this has a structure of quotient vertex algebra and has a chance to be Lis. In fact, it's known that this one is Lis if and only if it's integrable as a representation of G hat. So the Lis condition can be considered as a generalization of integrability condition. And if this happens, the category of module is exactly the category of integrable G hat module of level K inside the category O. So this is certainly a semi-simple category. So this case, this is a rational as well. So this nice vertex, this is an example of basic example of nice vertex algebra and correspond to the Wess-Zumino-Witten model. So we'd like to know when a W algebra can be Lis. And to study this, I'd like to introduce some notion. So for any vertex algebra, you can associate with it some certain quotient space, which has a structure of usual Poisson algebra, the finitely generated Poisson algebra, which is called the Zuse-Shitsu algebra. And it's because it's a Poisson algebra, you can just take a spectrum, and we call this associative variety of a vertex algebra. Now, what you can show is that the V is Lis if and only if this finite dimensional variety is zero-dimensional. So you don't have to look at the whole vertex algebra, but you just have to look at this finite dimensional variety to see whether it's Lis or not. Okay, for example, the associative variety associated with affine Katsumori algebra, affine vertex algebra is just a G star. So this corresponds to the fact that affine Katsumori algebra is affinization of a Lie algebra, finite dimensional Lie algebra. And so the associative variety of the simple quotient is a subvariety of G star, which is G invariant and conic. And as I said previously, this is zero if and only if this one is integrable. And the associative variety for the double algebra is so-called the Schroeder slice of this given nilpotent element, which is a affine subspace, which is a affine transversal slice to the G orbits defined like this. Okay. Now, so universal this double algebra is never Lis because its associative variety is a Schroeder slice, so it's not zero-dimensional at all. But if you take a simple quotient, it has a chance to be Lis. And so the associative variety of simple quotient is a subvariety of the Schroeder slice, which is invariant under the natural sister action, which contracts to the point F. So this is Lis if and only if this associative variety is the point F. Now, one can show that this simple quotient is a quotient of the reduction of the simple affine vertex algebra. And what you can show is that the Hamiltonian Dirichlet-Sokolov reduction is compatible with associated variety in this sense. So the reduction of the variety of the reduction is the intersection of the original associated variety of simple affine vertex algebra with the toroidal slice. So this in particular means if this is not to 0, if this variety is non-empty, and because it's invariant and this is the action, this happens if and only if this contains a point f, and because this is the invariant, so this happens if and only if this contains a closure of the corresponding nilpotent orbit, and if the associated variety is exactly the closure of the corresponding nilpotent element, by the transversality of the toroidal slice, intersection is a point wave. So the reduction of the simple one is this, so it's simple quotient of the double algebra. So as soon as if you find simple affine vertex algebra whose associated variety is a closure of a nilpotent element, you get these double algebras. So now you want to get some nice double algebra from nice affine Katsumudi algebra representations. And of course, the most nicest representation of affine Katsumudi algebra are integral representation. But as I said, the associated variety of integral representation is 0. So this doesn't satisfy this condition. So the Dirichlet-Sokolov reduction kills all the integral representation. So you have to study more general representations to obtain a nice double algebra using a Hamiltonian reduction. And in fact, there is a nice class of representation of affine Katsumudi algebra, which are called admissible representations, or Katsuwakimoto admissible representations. So this admissible representation contains all the integrable representation, and much bigger, and satisfy nice properties such as complete reducibility and modular invariance. And so in the case of this vacuum representation, this is admissible if and only if the level is a rational number of this form, satisfying some condition. And what you can show is that which was conjectured by Fengi and Frenkel, was that if this is admissible in the sense of Katsuwakimoto, associated variety is contained in the nilpotent cone of G. And in fact, its associated variety is irreducible, which means that there exists a nilpotent orbit such that the associated variety is exactly the closure of this nilpotent element. And this nilpotent orbit can be described explicitly. So by previous theorems, we immediately obtain the following statement. So if LKG is admissible affine vertex algebra, there is some nilpotent orbit whose closure is associated variety. And if you take nilpotent element from there, you obtain at least a simple affine double algebra. So each admissible affine vertex algebra produces exactly one at least a simple double algebra. So we are now in particular interested in the principal nilpotent element case, in which case the closure of the orbit is a whole nilpotent cone. And when this associated variety is a whole nilpotent cone, this affine vertex algebra is called non-degenerate. And most of the case, the admissible representation are in fact are non-degenerate. And so by the previous theorem, if this one is non-degenerate, then the corresponding double algebra, principal double algebra is least. So you want to know next whether it's rational or not. And so this was conjectured by Frankel, Katz, and Wakimoto in 1992. And in fact, this is true. So if you take any non-degenerate admissible affine vertex algebra, you get rational simple double algebra. And for SL2, this rational double algebra is exactly the so-called minimal series of the Virasoro algebra, which appeared in the work of BPZ. So this extends the minimal series of the Virasoro algebra to any simple real algebra. And this theorem is proved based by the proof of this statement is based on the following assertion. So, as I showed, you cannot really study double algebra directly. So you want to deduce result for double algebra from a result of Katsumuni algebra. And so in this case, you show first the corresponding affine vertex algebra is rational in some sense. And from this, you get the previous theorem. Anyway, so this is how this proof is done. Now I'd like to talk about, so far I talk about basically conjectures from the last century, but there's some recent development involving double algebras, more generally vertex algebra. So I'd like to talk about this. So there's several aspects of new development, but one of it is so-called 4D, 2D duality. Recently in physics, these physicists, Bean, Lemons, Liendo, Pires, Rastelli, and Van Lies, constructed a map or functor from the category of 4-dimensional n equals to superconformal field theory, whatever it means, to the category of 2-dimensional conformal field theory, which is the same as a category of vertex algebra. So they reduced somehow dimension by 2, so from 4D to 2D. And this functor satisfies, among other things, so there's certain important invariant or observable in the 4D theory called the Schur index, which is certain Q series. And this Q series is exactly the character of the corresponding vertex algebra. So what is nice about this is that so in conformal field theory, the Hilbert space is an irreducible representation of large algebra, so which is just a vertex algebra. But in 4D theory, we don't have such a large algebra. So Hilbert space is a direct sum of smaller representation. So you cannot really use representation theory to compute such an index. But if you use this functor or map, you can compute this numerical invariance. Now, so this is quite large class of superconformal field theory. So you get, by applying this functor, you get many, many vertex algebras, many interesting vertex algebras. And we'd like to know how the vertex algebra coming from this 4-dimensional theory look like. And there's some relation between 4D theory and 2D theory. One of it is the relation between central charge. The central charge has some value which takes positive value for unitary theory. And so this is central charge for the vertex algebra, and this is central charge for the corresponding 4D theory. And there's a minus sign here. So if you start with a unitary theory, you end up a non-unitary theory. So because physical theory is unitary, so vertex algebra obtained by this map phi are never unitary. So in particular, this familiar integral representation never appear by this correspondence. So you have so there are some exotic vertex algebra appear by this correspondence. And the main example of vertex algebra considered by these people, the simple affine vertex algebra of types D4, E6, E7, E8 at this level, which is in fact my negative integral level, and this is non-rational, non-admissible affine vertex algebras. And so another thing I want to talk about the Higgs branch. So this is another important invariant of four-dimensional theory. So this is a certain affine algebraic variety that has a hyperkähler structure in its smooth part. So in particular, this Higgs branch of the 4D theory is a symplectic variety. And in the case of previous examples, so the 4D theory corresponds to these vertex algebra the minimal nilpotent topic closure in these W-algebras. And Amuro and I studied this affine vertex algebra by a different motivation, and we showed that the associated variety of this one is exactly the minimal nilpotent topic closure, which coincides with the Higgs branch of the 4D theory. So in this case, associated variety of the vertex algebra and the Higgs branch of the 4D theory coincides. And the physicists believe now that this is not a coincidence, and in fact, for any 4D n equal 2 superconformal field theory, we should have the Higgs. The Higgs branch of the 4D theory should be isomorphic to the associated variety of the corresponding vertex algebra. So this is rather surprising because a vertex algebra is a purely algebraic object, and we are supposed to recover the geometric invariants such as the Higgs branch. And I should remark this Higgs branch conjecture is a physical conjecture because Higgs branch, well, for the theory itself, is not mathematically defined in general. And the Schur index itself, so because for the theory is not really defined mathematically, so this is a physical conjecture in general. And also, there's a close relationship between Higgs branch of 4D theory and Coulomb branches of three-dimensional gauge theories, whose mathematical definition has been given recently by Braveru and Finkelbaum and Nakajima. So in 4D, 3D duality, Higgs branch and Coulomb branch are switched. Okay. So in general, associated variety of vertex algebra is only a Poisson variety, is not symplectic. So the vertex algebra coming from 4D theory should have some special property. So it's natural to ask what kind of property it should have. And we call vertex algebra quasi-leaf if associated variety has only finitely many symplectic leaves. And so, of course, these vertex algebras are quasi-leaves because this vertex algebra has associated variety as a point, and the point is a trivial symplectic variety. And simple affine vertex algebra is quasi-leaves if and only if its associated varieties contains an nilpotent cone. So, in particular, admissible affine vertex algebra are quasi-leaves, and also the simple affine vertex algebra correspond to the D4, E6, E7, E7 at some strange level I showed before. And also, what is more importantly, physical intuition expects that the vertex algebra coming from 4D theory should be quasi-leaves. So this is not a sufficient condition for a vertex algebra to come from 4D theory, but it's one of the necessary conditions. Seems to be necessary condition to come from 4D theory. And what we can show is that if V is quasi-leaves, we can show that there are only finitely many simple ordinary V module. This means that the ordinary module means that the module whose character makes sense. And for any finitely generated ordinary V module M, this character converges to a holomorphic function on the upper half plane, satisfies a differential equation called a modular linear differential equation. And so modular linear differential equation appears in the theory of modular forms, and the solution of the space of the solution of modular linear differential equation is invariant under the action of SL2D. So this means that the character of quasi-leaves vertex algebra satisfies certain modular invariance property, and because vertex algebra coming from 4D theory should be quasi-leaves, and the character should coincide with the Schur index. So this means that the Schur index of 4D theory have some modular invariance property. And this is something conjectured by physics. And as far as I understood, this property cannot be proved in any other method. Okay, now, as I said, Higgs branch conjecture is a physical conjecture, but there are class of 4D theory where everything is mathematically defined. So this is a class called the theory of classes, which was introduced by Guyot, where this S stands for 6. So this theory comes from even higher dimension 6. So you reduce, compactify on a Riemann surface the 6-dimensional theory to get the 4-dimensional theory. So anyway, so you can apply the map phi constructed by Rastelli et al. And to obtain certain vertex algebra. And these form a certain special class of vertex algebra, and they are called the chiral algebra of classes. So this is a very interesting class of vertex algebras. And so Higgs branch, in this case, describes mathematically in terms by Mowa-Tachikawa. So Mowa-Tachikawa, there was a conjecture on the existence of 2D topological quantum field self whose targets are symplectic varieties, and which was recently proved by Braverman, Finkel, Varg, and Nakajima. And so you get by this 2D TQFT, you obtain many interesting kinds of symplectic variety, and these symplectic varieties are in fact Higgs branches of the class, theory of classes. So Higgs branch can be described purely mathematically. And lastly, all conjectures that the chiral algebra classes can be also described similarly in terms of two-dimensional topological quantum field theory. I believe Tachikawa talk about this conjecture on the background in this conference in math physics section. Anyway, so let me describe the conjecture. So we introduced the following category, which I call the category of vertex algebra. Also, I call this a category of vertex algebra. Objects are not the vertex algebra, but the complex semi-simple groups. But a morphism from G1 to G2 are a vertex algebra, which admits action of G1 hat and G2 hat as a critical levels. So G1 and G2 are the Lie algebra of G1 and G2 respectively. And so this affine algebra action should be compatible with a vertex algebra structure. So you should have a vertex algebra homomorphism from corresponding vertex algebra. So anyway, so this one is a vertex algebra equipped with the action of G1 hat and G2 hat as corresponding critical levels. And so this may look strange. So I have to explain how you compose two morphism from G1 to G2 and G2 and G3. What you do is you consider a tensor product of these two. Because these two admit action of G2 hat, you can consider diagonal action, which has level minus 2 times H2 check. And so at this level, you can consider corresponding semi-infinite cohomology with respect to the action of G2 hat. And this gives a certain vertex algebra. And because we did not touch the action of G1 hat and G2 hat, D3 hat, we still have action of G1 hat and G2 hat, and this satisfies this problem. And you may ask what is identity morphism from G to G, and but you find easily from a result of Arkhipov and Gascoigne that the identity morphism from G to G is what is called the chiral differential operators on G as a critical level, whose associated variety is canonically isomorphic to the cotangent boundary to G. And this category is a monoidal category, where a tensor product of objects is just a direct product, and the tensor product of vertex algebra is just a tensor product. Now, so because you want to describe, you want to use two-dimensional topological quantum field, so you consider the category of two bodisms. The statement is that for each semi-simple group, there exists a unique monoidal functor from the category of two bodisms to the category of vertex algebra, which I introduced. And the objects of two bodisms is just a finite union of S1 circles, and each S1 should go to this given group G. And the cylinder, which is identity morphism from S1 to S1, should go to the identity morphism from G to G, which is a chiral differential operator on G. And the real condition is that the cap, which is a morphism from circle to the empty set, should go to the Dirichlet-Sokolov reduction of the CDO as a critical level. And so by applying this functor, you get many kinds of vertex algebra as an image of two bodisms. And these are exactly the chiral algebra of classes. So this describes chiral algebra classes. And moreover, by taking associated variety, we can recover the functor from the category of two-bodism to the category of symplectic varieties constructed by Bravelian-Finkel of Nakajima by using the geometry of fine Grassmannians. So this theorem not only lifts the construction of Bravelian-Finkel and Nakajima, but also proves the Higgs branch conjecture for the theory of classes. Okay, thank you very much.